I have a question for you.
Yes, ma'am.
Am I going to guess that from because the next test is not for another, I think he said November 20th.
20th. Yeah, that sounds right. Uh-huh.
So 6, 7, and 8, is that all of it visual like that?
Well,
Like what you're describing?
six definitely is. Six definitely is. Seven is confidence intervals, so there's quite a bit of that because it builds on itself. Eight is hypothesis testing, which is less visual in some parts because it's not as visually dependent, but it does depend on some of those aspects for part of it. Hypothesis testing in chapter 8 has more to do with I have a situation, I have a hypothesis about that, like an assumption about whatever the question is that I ask you.
Mm-hmm.
And then based on I gather data, either they give me the actual numbers and I have to number crunch a bunch of formulas to get specific values out that I then put in a formula. And based on that formula, I then have a piece of this analysis to do based on the curve. Um, but it has, so that's less visual in that sense. But 6 and 7 are heavily dependent on understanding the normal curve itself. So
So
I
it's not exactly a square then, right?
no, I'm not sure where you got the square from. It's
No,
Z
I'm
squared, but
just asking, is it like a table, a square, or
no, it's actually okay. So the best way I can describe what it looks like for sighted people is think of walking in a place that's flat and then you walk up a really steep hill
yeah.
and then you walk down again
Oh,
the other
yeah,
side
yeah.
of the hill. It's
Mm-hmm.
it looks like a stylized version of a hill like that. That's what the curve looks like visually. So there's a flat part on either end, and then it gets increasingly steeper till you get to the top. And then, which is in the middle of the hill, by the way, yeah, you
And
get
then
to
it
the
starts to
top,
curve
and then
down.
yeah, and then it curves down in the same way at the same slant and comes back down. It's what we, if you think of the top of the hill before you start to descend as the peak, okay, that
Mm-hmm.
would be for us, that would be the mean of the distribution. That would be the exact middle of our distribution. So the distribution is a curve. It's a graphical representation of what data that are what we call normally distributed look like. Normally distributed is a phrase that you're going to hear over and over again. And when you hear that phrase normally distributed, what I tell students to think of when you hear that or when you see that is to think of this hill curve that I just described, because normal refers to the shape of the curve that you're seeing. Not all curves are normal curves. Some of them are skewed or they're rectangular or they're other shapes, but normal curves are always shaped like those hills that I described to you.
Mm-hmm.
And so normal curves have properties, things that make them distinctive
Mm-hmm.
and make them characteristic of other kinds of things. And that has to do with the mathematical properties of of the data that make them fall into this kind of distribution itself, which is kind of beyond the scope of this class for the most part. But one of the properties of normal curves is that if you think of that top of the hill that I described to you,
Mm-hmm.
the highest point on that curve is, if you think about, so you're standing on top of the hill, right? There's a point on the ground below you, directly below where your feet are. That is what we would call the horizontal axis if we drew it. So we have a line under it. And that point directly underneath your feet would be the center of the curve. The center where that high point is, that's the center of the curve. That center is where the mean is. If it's a normal curve, the mean, the median, and the mode are all at the center of the curve. That's one of the properties of normal distributions. And why that's important is we're going to have two kinds of normal curves. Two kinds of curves that are shaped like these hills. We have what we call the standard normal distribution, and we have the normal distribution. Now that additional word standard adds some very specific information. If it's a standard normal curve,
Mm-hmm.
then the center, that point right below where your feet are,
Mm-hmm.
is 0.
So the
And
center is always 0.
if it's a standard normal curve, yes. If it's a standard normal curve. And standard normal curves are where we usually start teaching z-scores from. So standard normal curves have a mean of 0, and then we have this other descriptor of a standard normal curve, which is how spread out our data are from the center. How spread out are they?
Mm-hmm.
It's called the standard deviation, which I think you've heard before. The
Yes.
standard deviation is, think of it as if I take all the values of the data
Mm-hmm.
and I were to figure out how far they are from that mean point, from that middle point where you're standing.
Mm-hmm.
Some of them are going to be very close and some of them are going to be further away, right?
Mm-hmm.
Think of taking, and some of them are going to be in front of you, which would be to the right of you
Mm-hmm.
visually. If this was a flat piece of paper, the points that are ahead of you or that are downhill from you, if I can say that, would be to the right, and points that are back the way you came behind you, if you were going to
Mm-hmm.
down the hill backwards, would be to the left of you. And those are significant because we have, remember I said the middle is 0, right? So to the
Yeah.
left of 0, we'll
Mm-hmm.
have negative scores. And to the right of 0, we'll have positive scores.
Okay.
So where z-scores come in to the picture, because you said you knew it had something to do with the z-score, right? Where z-scores come in is that they measure the, so I talked about the standard deviation as being the average the average distance from the mean that you are. Remember, the mean is the middle where you're standing. So the average distance from the mean. Some of them are closer, some of them are further, some of them are downhill from you on the right, some of them are downhill if you were going backwards on the left. But
Okay.
you take all those data points, you average how far they are from the mean, you add up all those distances, and then you do a bunch of calculations, and that average distance is roughly what the standard deviation is.
Okay.
And it turns out that for a standard normal distribution, this is, remember I said normal distributions have properties. They have things that define them. It turns out that for a standard normal distribution, that the mean is 0 and the standard deviation is 1. So they average 1 unit away from the mean.
Mm-hmm.
Okay.
Okay.
Now, just to clarify and just to make sure that you are aware, because this um, this section deals with the standard normal distribution. Okay. So
Oh.
you don't have anything else in this section. But if they don't have the word standard in front of it, if it's just a normal distribution,
Mm-hmm.
the mean is still in the middle, but it's not 0. It's usually whatever they give you. So I could say something like the distribution of IQ scores for a group of college students is 100 with a standard deviation of 15, right? I could say that their scores are normally distributed with a mean of 100 and a standard deviation of 15. I wouldn't call that a standard normal distribution because the mean is 100, it's not 0. Okay. And so the reason that I put that concept in here, we're not going to go into it in a great deal of detail, but the reason that I put that in there is that z-scores, which is what you started learning about,
Mm-hmm.
are also called standard scores. So what z-scores do, among other things, z-scores do a lot of things, but what z-scores do, among other things, is they provide a means to take a, a piece of data from a normal distribution
Okay.
and superimpose it on a standard normal curve. So if I describe to you there's a mean of 100 and a standard deviation of 15, I could take that score, like let's say I had a student who scored 118 on the test. I could
Mm-hmm.
take that score. I could do a calculation with the z-score, which is the score minus the mean, which would be 100 in this case, and divide it by 15, which is the standard deviation. Get what we call a z-score for it, and then use that data and put it on a standard normal curve. That's why that's important.
So the score of what that person got on the test minus or divided by,
No, minus the mean, you're correct. So the score minus whatever the mean is,
which is 15, right?
118 minus 100
Oh,
would be 18.
okay.
divided by 15.
Okay.
That z-score, I can then take that z-score and use it on the standard normal. The reason that that becomes important is that in your calculator or your charts, because there are also charts that help you read these, okay? But
Oh,
more often than not, no, more often than not, when we teach it, we use the calculator for it.
okay.
But there are charts back when, before we started teaching everything with the calculator and the computer, and we didn't have calculators that computed all these things, when I started doing it, we didn't have, well, we did have, but we didn't use graphing calculators to calculate all that. We used the tables.
Oh, wow.
So what they did is, see, they didn't want to have to construct a new table every time the mean and the standard deviation changed, right? So let's say I have another situation and it's like, okay, I'm talking about a group of older adults, and I'm talking about the age at which they retire. And I say the mean age at which they retired was 68 with a standard deviation of 2 years, right? I would need a whole table for that, a whole different table, because now the mean is different from the standard deviation. See? So um, all of those spaces under the curve would be different now, right?
Mm-hmm.
So that's why the z-score, the standard score, is such a big deal, because it allows me to take data from whatever curve I have and standardize it, meaning superimpose it on that curve. And I can use those same charts. I don't need every time the mean and the standard deviation changes, I don't need another chart. I just need to figure out where on the curve I am. Where on the hill am I standing in relation to the top? If I'm standing downhill from you, I'm positive somewhere, okay, depending on how far down the hill I am. If I haven't started climbing yet and I'm behind you, then the curve is not very steep just then, right? But I have a z-score there. It's a negative z-score, right? But I can find out where I'm at. That's why that's important. So that's kind of the background on z-scores, standard scores, and the properties. There's more properties than just those, but those are some of the main ones.
That's a lot to swallow.
It's a lot of information. I really thought about how to describe this to you, and I hope I at least gave you
It helps a little bit visually as
some
I
idea.
imagine it. So far as your analogy of using a hill and climbing the hill from one side to the other,
Mhm.
and you're giving me the interpretation of saying that I'm in front of you and you're behind me, and how that would look a little bit. It's a little
Yeah,
still a little fuzzy, but yeah.
no, it's hard, like, and the thing with me is like, how do you translate that? Like, it's frustrating for me, because it's like, in a way, like, and I've been teaching it, so it's like it's obvious, but how do I it feels like a giant translation, and I don't know how to translate that. But I really I hope I managed to convey something because
You did. It's just like the way he described it yesterday was, or for the last couple of days, was which part is how much of one side is shaded.
And we're gonna talk about that too, but I needed to give you some sort of like conception of what this is first
And
before.
I'm like, how am I supposed to know which part is shaded?
Exactly. Somebody's gonna have to describe that to you. You're not gonna know because or you're gonna have to be able to feel. That's why I said, like, do they have a means for you to feel that or describe? Because you're not gonna know. That's when we start, when we teach this section, besides kind of the overview that I just gave you of the hill and the properties and the center and left and right, positive,
Mm-hmm.
negative z-scores, besides all that, the next thing they do is they give you diagrams of the hill. So you have a bell curve, you have a normal distribution, a standard normal. They have a line. So you're standing at the top, they have a line. Now, they might not have the line in the center, okay?
Mm-hmm.
They'll have a line wherever you're standing on the hill in relation to the top. So the top of the hill is always the center of the distribution. That will help you, okay? So the top of the hill is the center. Visually, what they'll do is they'll have a line based on where you're supposedly standing in relation to the top.
Uh-huh.
So I'm going here from west to east. So I'm going left to right, which is the way the number line goes. The left side has negative numbers, the
Mm.
middle is 0, and the right side has positive numbers, okay? So when you start out on the flat ground on the west, that's like 0, and then you're going up the hill, like 0 area. So because you haven't left the flat ground yet, you're walking up the hill. At some point, you're going to stop walking, maybe before the top or maybe after the top on the way down. But wherever you're supposed to be standing, there's going to be a line there visually for the person looking at it.
Mm.
And they're going to want you to find, now they can ask this a couple of different ways, but typically the way they start is they start with a z-score. So let's say they start with like negative, and it's usually 2 decimal places. So let's say they start with negative 0.4, right?
Mm-hmm.
That means that you're walking up this hill, you haven't made it to the top yet. You're a ways from the top, but you're at negative 0.4. So you're on the left side of the top of the hill, so to speak. So you haven't made it to the top yet.
Doesn't sound like I got very far, according to what.
Well, okay, so remember that, okay, I should explain something else to you because I haven't explained this yet. So we talked about 0, right?
Mm-hmm. Mm-hmm.
So here's the thing about z-scores, okay? We also have, you have to think about, so here we have the hill, we talked about being on top of the hill, right? And I want you to think about there's, like I said, there's ground below you, or you would be sinking, right? There's ground below you. So we think about the amount of dirt or sand or whatever this hill is made from that's under the curve, that's holding you up. the amount, the dirt that's under that curve, right? That if I mark a certain point, okay, the amount of dirt that is either behind, like underneath you, but behind you or in front of you is what we term the area under the curve.
Okay.
And the area under the curve, the total area under a curve, whether it's a standard normal curve or a normal curve, any normal curve, any hill-shaped curve like this, the total area under the curve is 1 unit or 100%. Okay? So
Mm-hmm.
if I were standing right at the top of the hill with the ground below me, okay, like below me on the flat ground, right? If I were standing at the top of the hill, there would be 50% or 0.5 of the area behind me, underneath the hill, holding me up. And there would be another 50% of the area under the curve, under the hill, holding me up. So it would be 50% on either side of me because I'm right in the middle, okay? That z-score would be 0, but the area under the curve would be half on either side, depending on what.
On either side of the zero. So the zero is always in the middle, in the center.
Yes,
Okay.
yes, because I'm yeah, that's good. So I'm talking about two different things here, okay?
Mm-hmm.
So the area under the curve is what you're going to use z-scores to help you find, because the area, the thing about the areas that we're going to be finding with the calculator, or that we would have used tables to find, whatever we do, but the thing about the area is those areas under those curves correspond to probabilities of things happening. So if I go back to my example about the college students who have a mean IQ of 100 with a standard deviation of 15, right? I could ask you, what is the probability that, and this is again beyond this lesson, but this is just so you can conceive of this a little bit. I could say, what is the probability that a randomly selected student has an IQ of 118 or below, right? So what I would do in that case, the first thing I would do is take his IQ score, which is 118, do my little formula for the z-score, which is 118 minus the mean, which is 115. That's 3, 118 minus 115. And then I divide that by the standard deviation, which is 15. Okay, so okay, that's 3 over 15. That comes out to 0.2 as a z-score, okay?
Mm-hmm.
Now that 0.2 or 20% means that since that z-score is positive, okay, that means that I've walked up the hill, I've hit the top, and I'm walking down, okay, and I walk down 0.2. So I walk down 20%, okay, on the east side of the hill, because remember my hill goes from the west to the
To the
east,
right.
from the left to the right. So I walk down 20% from the top being 0. Now what I do is I take my calculator and it does its fancy calculation and it
Mm-hmm.
looks at those charts that those people created with all those areas in it, right? I do the calculator calculation and I find, so in this case, my shaded area, if I was looking at this visually and somebody were saying the shaded area is this, what you would have is where you're now standing 20% of the way down on the right,
Mm-hmm.
that spot would be, you would have, think of it like having maybe a rappel rope or a bungee cord or something like that to the ground.
Mm-hmm.
You would have a line that would fall from your hand or your arm, wherever, to the ground.
Mm-hmm.
And that line would mark where you're standing. And that line would correspond to a z-score of 0.2. Okay? And there would be dirt under the hill from the part behind you, which would be the area that under the curve that was less than that z-score, because lower z-scores are behind you, right?
Mm-hmm.
And higher z-scores are in front of you. So the lower z-score, I'm sorry, the area under the curve from your z-score that includes the area from your position to the start of the hill would be what we wanted to find. The probability that if you were standing at that location, what is the probability of choosing somebody with your IQ score or below you?
Okay.
And we would put that in the calculator. That would be a probability. Now, because you're standing on the downward slope, right? And because the hill represents 50% of the area on either side of it, right?
Mm-hmm.
We may not know exactly what that number is, but we know it's more than 50%. We know that because if you were standing on the crest of the hill, the top, and you dropped a line from your arm or your hand, whatever, to the ground, that would be a 0 z-score because you'd be right on the mean, right? But it would also be 50% of the area would be behind you and 50% would be in front of you, right? So if you were walking on the downhill slope, there would be more area behind you than in front of you.
If you're on the downward side.
Exactly, if you're on the downhill side.
Okay.
Okay, does that help a little bit?
A little, yes.
So that downhill side is a positive z-score because you're to the right of the mean, to the right of the middle. And z-scores that are negative would be on the uphill portion behind you.
Okay. That's the negative side.
Yes. Mm-hmm.
And where I'm at, I'm on the positive end of the spectrum.
That's correct, just because of the situation that I described, right?
Mm-hmm.
Now, if I described a situation and I said, the scores of individuals are normally distributed with a mean of 100 and a standard deviation of 15. And I said Sally has an IQ score of 80.
Okay.
What is the probability that I randomly select somebody with Sally's IQ or lower, right? Now, the mean is 100 here, and her score is 80, right? So, where are you standing on the hill right now? If you're standing where Sally is, where are you standing?
So she's at
She's at
80.
80. Uh-huh. And the mean is 100. So where are
Mhm.
you?
You'd have to subtract 100 from 80.
Okay, that's 20.
That's 20%. And then you divide that.
20 divided by 15.
The number is always 15.
No, I just gave it to you in that example.
Oh.
It varies. So it's always the mean, it's the score, whatever score the situation is,
Mm-hmm.
minus whatever the middle is, wherever the middle is,
Yeah.
divided by the standard deviation.
Okay.
So the score minus the mean minus the middle over the standard deviation or the spread.
And then you divide that by,
In this case, that would be 15. So you'd have 100. I'm sorry, you'd have 80. 80 minus 100, which would
which is
be
20.
negative 20, because her score is lower, right?
Okay.
Her score is lower. So which side of the hill are you on? Are you going up the hill or down it?
Down.
No, because the top of the hill is what? The top of
That's
the hill
100.
is 100. She's at 80. So she's behind you. So you would have climbed up past her. Okay, so she's behind you. She's on the uphill side. Like she's uphill from you right now. Like she's behind you, but you had to pass her on the uphill side. You're still climbing up the hill.
Okay.
Okay. She's behind you if you're at the peak, right?
Mm,
But if you're standing with Sally, if you're maybe it's easier if I say if you're standing where Sally is, you haven't gotten to the top.
no.
So you're on the downhill, that the uphill side, because you're still climbing up to get to the top.
Mm-hmm.
She's on the left side,
Mm-hmm.
and her z-score is negative. So it's 80 minus 100,
It's 20.
negative 20 over 15. And that is negative, um,
So is it 15 over 20? Or is it?
yeah, well, it's negative 20
Mm,
over 15. So you're
okay.
at negative 1 and 1/3, negative 1.3. Okay, so you'd be at a negative score. Now, if her score was 120, 120. So
Mm-hmm.
now she's past the top of the hill because the top was 100. She's past the top. She's going down the hill.
Mm-hmm.
She's at 120. Now her z-score is 120 minus 100, which is 20, over 15. That's positive 1.33. Now
Okay.
her z-score is positive. She's on the downhill side because she's already climbed to the top and she's on her way down.
Mm-hmm.
So she has a positive z-score
Right.
at that point.
Okay. That's a lot to absorb, like I said.
And so what we're going to be doing in the lesson is basically looking at a bunch of normal curves.
Mm-hmm.
And there's two things that we're going to be doing. One is we're going to be finding how much dirt is under the hill that the part of the hill that you're standing on. Like I talked to you about, how much dirt is under it. That's one thing.
Mm-hmm.
The other thing is, we can also ask you, it's kind of weird. This is where my analogy breaks down just a bit. But
Yeah.
the other part that we can ask you is, okay, supposing that we don't know the z-score, so we don't know exactly where you are in relation to the top or the bottom of the hill.
Mm-hmm.
But we know how much dirt is either in front of you or behind you. Now, if you think carefully about this, if we know how much dirt is in front of you or behind you under the hill, right? That has to locate you somewhere. So
Mm-hmm.
it's a different way to ask the same question. Okay? It's a different way to ask the same question. If I say to you, okay, well, here I am, and in this case, I know that, and we're going to get into this more, but if I were to ask you, okay, I need you to find the z-score. So I need you to tell me where you are in relation to the mean from that distribution. If I said, okay, well, you're at 40%
Mm-hmm.
of the area is to the left of you. So
That's the 40%.
40% of the area is to the left of you or behind you, right?
Okay.
We know something without doing any calculations. We know you haven't reached the top yet because the top would be 50%, 50% behind you, 50% in front of you. So if I say there's 40% behind you to the left of you, I know that your z-score must be negative. Okay, I don't know what that is without doing a calculation, and I just did it here. Okay, but I know that my z-score has to be negative. So there's two ways of locating you, and there's, depending on whether we describe the situation as, okay, they gave me a z-score
Mm-hmm.
and I want the area to the left of that z-score. So the z-score is where you're holding the rope, it drops. Where does the rope drop in relation to the top of the hill, right? And then how much dirt is to the left or to the right of that. The shaded area that you're talking about,
Mm-hmm.
when you hear shaded areas, again, there's two ways to ask that question. But essentially, I think the easiest way for you to think about shaded areas for the analogy that I'm using here, and you can feel free to change this, embellish this, ask me questions about this. I don't think it would be very, maybe it would, but I think it would be more confusing if you tried to think of it as actual light and dark in terms of that shading, even though that's what it looks like visually. I think
Mm-hmm.
it's probably better if you think about you're on the hill, right? And depending on whether the person is describing the amount of dirt under, like the percentage of dirt underneath you, or the place where you're actually standing on the hill itself,
I see.
is think about holding that rope that I talked about, right?
Mm-hmm.
The shaded area that people are going to be describing to you is going to be in relation to that piece of rope that you're holding. So if I say to you, like, one of the questions on your homework is you're on the hill, right? And I want to find a z-score. Now, if I talk about finding the z-score, I'm talking about your location on the hill in relation to the top of it. Because remember, the top is
0.
right? So, so if I say to you, where is the z-score if 40% of the area, or 40% of the dirt that's holding up the hill
Mm-hmm.
is behind where your rope. So you have a rope, you drop your rope to the ground, right? And 40% of the hill is behind your rope now.
Mm-hmm.
What is your z-score? In that case, I've given you the area, right? And you have to give me the z-score. Okay. Compare that to this question. If I said, you're on a hill, you're on the hill, and you're at a location such that when you drop the rope down, your z-score is 0.4. Okay. Your z-score is 0.4. First of all, which part of the hill are you on? If you have a z-score of 0.4, are you climbing up the hill? Have you reached the top, or are you climbing down? If your z-score is 0.4.
Hmm. This is crazy. That's a lot of information. It's just so much to absorb.
That's okay. It's okay. So if you're at the top, what's your z-score?
That's 0.
Right. Is 0.4, is that higher or lower than 0?
I want to say lower.
0.4 is higher than 0. Think of it like money, right? So 0 would be $0, right? 0.4 would be 40 cents. So it's higher. It's a positive z-score, right? So if it's a positive z-score, what side of the hill are you on?
Left side.
I'm sorry, what?
Left side.
If it's positive,
Oh, I'm sorry, the right side.
you're coming down the hill, so you're on the right side. And so the shaded area, depending on what they tell you, that's where your rope is. You're on the right side of the hill, you've got a rope, right? And it drops at 0.4. That's where you are. Now, if I tell you that the shaded portion is to the left of you, then it would be everything behind you. Yeah? If I said the shaded area was To the right of you, it would be everything ahead of you.
Okay.
I think
Okay.
that would be the easiest way. I mean, it is a lot of directional terms to take in, but I think, and you can feel free to disagree with me. If something else works better for you, I'm fine with that. But I think that's a little easier way. It's a little more concrete than just thinking about shadows everywhere. Because shadows can come from anywhere, and so can the shaded areas. But I think this way gives you a little more concrete
Mm-hmm.
way of like in relation to what in relation to what are we talking about here. um but hopefully that gives you a little bit of a sense of what the chapter is on, and maybe the next lesson I can teach you a little bit about how to use the calculator to find those things, because it's not, the calculator itself is not that hard to conceive of. It's just about putting in the numbers. There's four numbers that we have to put in. There's two that are already there and two that we have to put in. And there's two different commands for it, depending on whether we're talking about finding the z-score, given how much dirt is under us, versus if I tell you where the z-score is, how much dirt are we talking about?
Mm.
So I don't know. I was confident in my analogy, and now I'm like, maybe it doesn't quite work as well as
No, 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 you're making sense. It's just
it's a lot. No, I know it's a lot because I had, while I was trying to describe it to you, I actually had my eyes closed so I could try to describe it better.
oh, and did it work?
A little bit, because I was picturing it. I'm a very visual learner anyway, so
Mm-hmm.
when I do that, I see pictures in my head anyway. But I was trying to consciously do that so I could maybe not provide details that weren't relevant. I don't know, but time will tell if I succeeded or not.
Yeah, yeah. We'll get there.
but at least but at least it was entertaining.
Yeah. Mm-hmm.
Thank you for coming to my movie. I hope you enjoyed the popcorn.
The popcorn's in the kitchen's not even ready yet.
I
So,
can just, what were you eating right now?
oh, I was eating some trail mix. That's what I was eating.
Oh, nice. Okay.
Yeah.
Nice.
Yeah.
Yeah, so I don't know. Maybe that will help you a little bit, but maybe that will help you.
It helps a little bit, but it's making sure to put the numbers in the right places and calculating everything
Well, yeah,
so it all comes out
that
right.
takes practice. That takes practice, but it's a highly visual. This portion is highly visual and it's highly concrete. So I just don't know, given that you don't have like any manipulatives or any form of input, it's
Mm-hmm.
just hard to know what I should. I mean, I'm really winging it here. So I,
Mm-hmm.
yeah,
Even if you are winging it, you're doing the best that you can, and that's okay.
yeah, and I'm having like, that's the frustration for me. Like I could sit here, I wouldn't mind describing it to you for another hour. I just don't think it would do a lot of good. You know what I mean? Like we can beat on it
No,
but it's just, and it takes a while to take in too. It does. It takes a while to
I
take.
don't understand what's the point of using these. Z scores. I get it, say like if it was a test and you're making calculations based on the scores, yeah. But in other cases, I just don't.
The application of a Z-score, you mean?
Yeah,
So,
that.
okay, so more broadly, what it is they have a lot of applications in a lot of fields.
Mhm,
So in an educational field, for example, like they'll do like a teacher will do this, or like sometimes in a healthcare setting they'll do this. Your teacher um might compare the classes and do a presentation
mhm,
and say, okay, the mean score for this test was 75. Okay. So half
mhm,
the people got more than 75 and half the people got less. The mean score was 75 with a standard deviation of, say, 5,
mhm.
right? So, what that does is it gives us a picture of where the scores fall. The majority of scores fall between 70 and 80, one standard deviation above and one below. There's
Did
proper
you say 78
70 and
and
70 and
8?
80.
Oh, 70 and
Like
78. Okay.
70 and 80, because I said the mean score was 75, right? With a
Mm-hmm.
standard deviation of 5 units. So
Mm-hmm.
what that does is it gives us a picture of where the majority of scores fall. And for teachers who grade on a curve, for example, the majority of, if they grade on a true curve, which most teachers do not do, then about 68% of the students would get C's and they would have scores between 70 and 80.
Oh,
There would
okay.
be an additional, there would be an additional group of people who were what we call 2 standard deviations away. So they would have scores between 65 and 70 and or 80 and 85 who would get B's. And then we go out from there and we figure out our C's and our D's. Now, another instance where standard deviations are used, they're used a lot in like medical situations. They use them a lot for normative growth, for example. So you go to the pediatrician and Sally has her 1 month checkup. You take Sally and they do all kinds of measurements on Sally. How long
Mm-hmm.
is Sally? How much does Sally weigh? Um, what is how much does she eat? Those kinds of things, right? And they measure her and they say, okay, Sally has these measurements, and they'll tell you, oh, base, you probably won't see it in the medical records, but they'll say, oh, Sally is, you know, 1 standard deviation below her age level, right? So she's, most kids at that age would be this length, and there's some variation in it, and she's here, so she's below that, and they might, depending on where she is on the growth chart, they might give her additional formula, or they might recommend watchful waiting, or they might do any number of things depending on what they think is causing that abnormal or that
Z
irregular
score.
kind of growth, right? So that's
Mm-hmm.
another, or another thing they'll talk about, like IQ is another big one, right? IQ scores are like that, but it's also things like, okay, I'll give you a kind of a funny example, but it's based on a real example that I did with a class one time. The teacher was explaining, it was a stats class, and the teacher was explaining outliers, which we've talked about a little bit, but we haven't really gotten into. But she was explaining what outliers are.
Mm-hmm.
Outliers are basically extreme scores that are extremely low or extremely high for the data, and there's mathematical calculations for that, right?
Mm-hmm.
Statistically, usually an outlier is any data value that's beyond two standard deviations from whatever the mean is. So either here you are at the middle and you're like fifth, you're about 5% of the way up the hill and you've got another 40% to the top, or you're almost down, you've got another 5% to the bottom. So you're on the extremes, right? Anything outside of you is considered extreme. So here was an example. And she asked me if I wanted to participate. And I said, well, I'm going to be an outlier in your study because of what I'm about to describe to you. So what she had everybody do was she had us all get out a piece of paper and take our dominant hand, whatever hand we were used to writing with, and write a bunch of X's on the paper for, I think, 30 seconds or something. So we wrote as many X's as we could. We counted up all the X's, whatever it was. And she put everybody's data on the board. And because, I mean, I can write and I can use my hands, but I don't have completely normal dexterity. So I expected it to be an outlier. Sure enough, like most people got like between 80 and 100. I think I had like 70 something, right? So I was a little bit of an outlier for that. Then she had everybody do it with their non-dominant hand, right? Now I have in my non-dominant hand, I have more spasticity in that hand. So I have more difficulty. I can manipulate it, but I'm like super slow. Like somebody with a broken arm could probably get it faster than I did. So I had like most people with their dominant hand, maybe if they had like 80, they were at maybe 70 or 65. I'm at like 30, right? So she does these data,
Mm-hmm.
and we're doing the data and we put it all together, and then we're considering my numbers, and it was a little bit, I wasn't
Ooh.
explaining.
Hold on a minute.
Message button. Slide to Celia Francis. Slide to answer.
Hello. Hello. I'm doing okay.